Okay, for our next topic here in Conceptual Physics AB, a little bit of mathematical background is necessary prior to treating those topics, specifically with what has to do with what is called a radian. Okay, a radian is a more mathematically precise way of describing an angle. Okay, let me introduce radians to you in the following way. Okay, how many degrees are there in a circle? There are 360 degrees in a circle. However, why are there 360 degrees in a circle? The reason is that that number, 360, is very close to 365 days in a year. But 365 is a difficult number to work with, so then therefore what we have done artificially is we've rounded 365 down to 360, and then therefore by definition there are 360 degrees in a circle. In other words, the reason why there are 360 degrees in a circle is because it's just a purely arbitrary human invention. There is instead a much more mathematically precise way of describing angles, and that is what is referred to as a radian. So let me now go ahead and describe radians to you. Okay, so to do so, what I'm going to do is draw a circle here, like so, and then let's say that right here is the radius of the circle. Okay, now what I'm going to do is draw a second radius like so, and when I do, I create, or as we say, subtend an angle on the diagram. That angle is right here. I'm going to go ahead and describe this angle as theta. Okay, and then on the circle, let me go ahead and connect these 2 points like so. When I do, I form a distance here on this circle. This distance is referred to as the arc length, and it's called the letter S. So the letter S here is what's called an arc length. Okay, now, let's say that I draw this diagram, much as I have done, such that S and R are the same thing. So imagine that the radius here is 10 centimeters, and imagine that the arc length here is also 10 centimeters. If S and R are the same thing, then the angle theta is called 1 radian. So let's say that S and R are the same. When we do, then the angle theta is equal to 1 radian. Let's say that I draw the diagram differently, however. Let's say I draw the diagram such that the distance S is 2 times the radius. So imagine that the radius is 10 centimeters, but imagine that S is 20 centimeters. Therefore, the angle is bigger. In this case, it's actually twice as much, and we then therefore refer to this as 2 radians. Okay, now with these 2 simple examples here, all that I'm actually describing is nothing more than a ratio. That ratio for an angle in terms of radians is written in the following way. An angle theta is equal to the arc length divided by the radius. Notice how this works for the 2 little examples that I have just done. For example, in the first example, S and R are the same thing. So if S and R are the same thing, they cancel each other out, and then we're just left with 1. And we refer to this as 1 radian. And then in the second example, if we write the numerator S as 2 times R, then you have 2R over R, and the R's cancel out, then you're left with 2. And we just refer to that as 2 radians. So an angle in terms of radians is nothing more than this ratio, the arc length divided by the radius. Okay, an angle written in this manner, by the way, has no units associated with it. The reason why is because it's basically a distance divided by a distance, and then therefore you end up with nothing. You end up with no units. It's what's called a dimensionless quantity. The word radian is actually nothing more than a name. It is a name that is given to this ratio here of the arc length divided by the radius. Okay, now how many radians are there in a circle? Those of you that are already familiar with radians may recognize the answer as 2 pi. But now let me go through exactly why that is. Okay, let me do a little bit of erasing here. And now let's switch to the lower board. And let's take a look at pi. Of course, everybody knows that pi is 3.14159, blah, blah, blah. But what is it about any circle that always gives us this number? Well, regardless of the size of the circle, if you take the circumference of that circle and you divide it by its diameter, you always get the same thing. You always get 3.14159, and we just refer to that fundamental constant of nature with the Greek letter pi. So whenever you take the circumference of a circle and divide it by its diameter, the diameter is twice the radius, you always get the same thing, regardless of the size of the circle. Now, notice that this description of pi looks pretty similar to this description of an angle in terms of radians. Here's then how you can link the two together. Okay, let me draw a complete circle here, like so, where here's the radius. And now let's go all the way around the circle. If I go all the way around the circle, this right here then becomes my angle theta, like so. And then if I do go all the way around the circle, notice that the circumference of the circle is equal to the arc length. So this angle theta in terms of radians is equal to the arc length divided by the radius. Notice that this here looks pretty close to this here. In fact, if I take this description of pi and take the 2 and move it up here to the left-hand side like so, I then end up with the exact same ratio as I do right here when describing the angle when going all the way around the circle. So the angle when going all the way around the circle then therefore is equal to 2 pi radians. So therefore, that's what this symbol here means. Therefore, the angle theta is equal to 2 pi radians. Now, 2 pi is about 3.14 times 2. That's about 6.28. And there's 6.28 radians in a circle. There's 360 degrees in the circle, but only 6.28 radians in a circle. So 1 radian is a lot bigger than 1 degree. 1 radian, by the way, is approximately what I drew on the diagram that is up there still on the top board. So suffice it to say, 2 pi radians is equal to 360 degrees. Okay, this right here is a little conversion factor that we can use, by the way, when going back and forth between angles in terms of radians and in terms of degrees. Usually what we do is we shortcut this conversion factor a little bit, though. What we actually do is we actually divide both sides of the conversion factor here by 2. What we do, we end up with pi radians is equal to 180 degrees, and this is a conversion factor which we can then use. Okay, now let me take you through some basic examples of using this conversion factor. Take a look at the lecture examples that I've posted for you in today's folder. Go ahead and copy down the first problem. I'm going to read it to you here on my screen. It says, convert the following from degrees to radians. Leave the answer as a multiple or fraction of pi, and then we have 4 examples here to look at, A, B, C, and D. Okay, let me go ahead and do some erasing here. Okay, so in this example, we're converting from degrees to radians. Okay, and the very first value that we have, A, is 45 degrees. Okay, what I have to do in order to convert this into radians is multiply by the conversion factor. Specifically, the way that we do so is we place the pi radians here in the numerator, and then we take 180 degrees and place it here in the denominator. For the examples that we have here in this problem, I'm going to go ahead and do the math by leaving the answer, as it says, as a fraction or a multiple of pi. So I'm going to leave the pi there the whole time as I do this process. Okay, now let's go ahead and simplify. How many times does 45 go into 180? 4 times. So if I cancel this and then cancel this and make it a 4, this then ends up being pi over 4 radians, and we just leave it at that. Similarly, for the other portions here of the problem, let's take a look now at B. B is 150 degrees. We're going to multiply by pi over 180. When I arrive at my answers, I'm always going to arrive at answers that are in terms of integers. So here's then how I do that for this example here. Okay, the common factor to these two numbers is 30. How many times does 30 go into 150? 5 times. How many times does 30 go into 180? 6 times. So then therefore, when I reduce this, I end up with 5 pi over 6. When you do these types of examples involving these simple types of angles on a unit circle, you then always write the answers as a fraction or multiple of pi, as I'm doing here. Okay, the other 2 examples as well. Okay, 225 degrees. We're going to multiply this by pi over 180. The common factor to these two numbers is 45. 45 goes into 225 5 times. 45 goes into 180 4 times. So then therefore what we're ending up with here is 5 pi over 4 radians, like so. And then the last one, part D, is 300 degrees. We're going to multiply this by pi over 180. The common factor for 300 and 180 is actually 60. 60 goes into 300 5 times. 60 goes into 180 3 times. So then therefore we're left with 5 pi over 3 radians as the answer. Okay, this process does take a little bit of practice when writing out these conversions from degrees to radians. Okay, then in number 2 here, we're just going to go backwards. Now what we're going to be given in number 2 are angles already in terms of radians, and then we're just going to convert them back into degrees. Okay, in order to do so, I'm going to erase the board here. Okay, I need to move the file here on my screen to access the example, so let me do that. And then once again, we have 4 basic examples here to look at, A, B, C, and D. So now it says convert the following from radians to degrees. Okay, the first one is pi over 3. Okay, now to convert this from radians to degrees, we once again multiply by the conversion factor, but in this case we take the reciprocal of what I did earlier. So now we multiply by 180 over pi, like so. Notice the difference here in these sets of examples as opposed to the previous set. Okay, this then, by the way, shows the advantage of writing an angle in radians as a fraction or multiple of pi, because when you convert it back to degrees, the pi's just cancel out. So it makes it easy to deal with mathematically, like so. And then 3 goes into 180 60 times. So this is a 60-degree angle, like so. Okay, let's take a look at the others. Okay, 5 pi over 4. We're going to convert this by multiplying by 180 over pi, like so. Once again, you just cancel out the pi here and here. 4 goes into 180 45 times. And then 45 times 5 is 225 degrees, like so. Okay, similarly for the last 2 examples, 7 pi over 6, you multiply that by 180 over pi. Pi's cancel out like so. 6 goes into 180 30 times. And then therefore you have 7 times 30. 7 times 30 then is equal to 210 degrees, like so. And then the last example, part D, 5 pi over 3, multiply by 180 over pi. Pi's cancel out, here and here. 3 goes into 180 60 times. 5 times 60 is 300 degrees, like so. So that's how you do these little conversions back and forth, and it does take a little bit of practice. There is a short handout assignment that you are to complete, and those problems that are on that handout are very similar to what you just saw me do here in these 2 examples. Okay, this is the mathematical background that is necessary to go into our next series of topics, which begins with the next lecture.